let's dive into this. We see these massive engineering projects, dams, bridges, skyscrapers, and we're just blown away by the sheer scale of them. But what's really fascinating, I think, is how some of the most brilliant engineering solves a problem that sounds surprisingly simple, but on a colossal level.
I mean, really think about it. Picture this. You're in a massive quarry or a mine, and your job is to move thousands of tons of rock from the bottom of a pit all the way to the top, every single hour. So what you do? Well, your first thought is probably easy, a conveyor belt, but you'd hit a massive wall really, really fast.
You see, a standard conveyor belt is pretty much just a moving trough. It's fantastic for flat ground, or maybe a tiny incline, but the second you try to point that thing steeply uphill, all your material, whether it's gravel, coal, you name it, is just going to slide and tumble right back down to where it started. Gravity's going to win that fight every single time.
So that brings us to our first big challenge. We've got to figure out a way to overcome this fundamental force that keeps everything stuck to the ground.
This really gets to the heart of the physics battle. There's this tipping point, right? It's usually around 18 degrees or so. And at that angle, the force of gravity pulling the material down the slope becomes stronger than the friction holding it on the belt. And just like that, your conveyor belt isn't a conveyor anymore. It's a slide. It's clear we need a totally new way of thinking.
And this is where the real genius kicks in. Instead of trying to fight a losing battle with an open belt, some very clever engineers came up with a brilliantly simple, kind of out-of-the-box idea.
They basically decided to put a lid on it. A sandwich conveyor uses a second belt, a top one, that moves perfectly in sync with the bottom one. The material gets loaded on, and then this top belt comes down and gently presses on everything, creating this moving sandwich that holds all the material locked securely inside.
And the difference this makes is just staggering. Look at this comparison. We go from being stuck at an angle of less than 18 degrees to being able to go up to 90 degrees. That's a straight vertical climb. Just by adding a second belt, you've completely changed the rules of the game. You're not fighting gravity anymore, you're trapping it.
But okay, inventing the sandwich idea is one thing. That's just the beginning. Now comes the really hard part, the math. Engineers have to calculate these enormous forces needed to pull off this vertical climb, making sure the whole system doesn't just grind to a halt or, snap in half.
So the first number they absolutely need to know is called effective tension, or TE for short. The best way to think about it is like this. When you're driving your car, the engine isn't just moving the weight of the car, right? It's also fighting against wind resistance, the friction from the tires, all of it. Well, TE is the exact same thing for this conveyor. It's the grand total of every single force the motor has to overcome.
So what's included in that grand total? Well, first and foremost, you've got the immense force just to lift all that material against gravity. That's the big one. But on top of that, you have to fight the friction from literally thousands of little rollers that hold the belts up. And you even have to account for the energy it takes just to bend those super thick rubber belts as they curve around the pulleys.
Once they've added up all those forces, they get the most critical number for safety, tight side tension. Just think of it as the spot on the belt that's being pulled the hardest by the motor. This number, T1, tells the engineers exactly how strong the belt needs to be so they can pick one that's tough enough for the job and won't fail.
This chart really paints a picture of what that motor is up against. I mean, as you can see, the friction from all the rollers and the energy it takes to bend the belt, yeah, those are real forces. But they are absolutely dwarfed by the main event, the raw power needed just to lift the material. That's where almost all the energy goes. Okay, so we figured out how much power we need to get this thing moving. But there's still one huge, nagging question about how this whole sandwich thing actually works.
Right? We've got a top belt and a bottom belt. But if you're going straight up, what's stopping a whole bunch of loose rock from just slumping down and pouring right out the back from between the two belts?
The answer is this wonderfully simple and elegant concept called hugging pressure. It is the secret sauce of this entire system. Here's an analogy. Imagine trying to hold a book up against a wall. You can't just set it there, it'll fall. You have to press it firmly into the wall. That pressing force creates friction, and that friction is what holds the book up. Hugging pressure is the exact same idea.
It's actually some really cool simple physics at play. The sheer weight of that super long, heavy top belt puts a constant squeeze on the material, and that squeeze generates a powerful frictional grip between the material and the belts. The success of the entire design boils down to one simple fight. The upward grip from that friction has to be stronger than the downward pull of gravity. As long as friction wins, the material is going up.
So the engineering check becomes this two-step process. First, they have to calculate the bare minimum amount of squeeze they need. They look at the material's weight and the angle of climb, and they ask, okay, exactly how much hugging pressure do we need to win this fight against gravity?
Pressure is what makes the whole magic trick work. So that pressure creates friction. And if you can generate enough friction inside that sandwich, it actually becomes stronger than the force of gravity trying to pull it all down. You're essentially creating one solid, cohesive unit that can be carried upwards without falling apart. You're tricking gravity, which of course leads to the big engineering question. How much pressure is just right? Because if you squeeze too little, the material slips and it all fails. But if you squeeze too hard, you're just wasting a ton of energy, and you might even damage the material or the conveyor itself. So how do you find that perfect sweet spot? Well, the relationship is actually pretty logical, and this chart lays it out perfectly. As the angle of the conveyor gets steeper, the force of gravity you're fighting gets stronger, so you need more of that hugging pressure. You can see here a gentle 30-degree incline needs a relatively low amount of pressure. But by the time you go completely vertical, a 90-degree lift, you need way more squeeze to keep everything in place.
Then, for step 2, they calculate the actual pressure their system is going to provide. This is based on the real-world weight of the top belt they've chosen for the design. This number represents the real squeezing force their machine will actually generate day in and day out.
And this right here, this is the moment of truth. If the actual pressure they can generate is equal to or more than the pressure that's required, then the design works. It's that simple comparison that gives an engineer the confidence to say, yep, let's build it. This thing can lift a mountain of rock straight up into the sky.
So, with all the forces calculated and the hugging pressure confirmed, all of this super complex analysis gets boiled down into a single, practical document, the final spec sheet.
And this is it, the final output. Every complex formula boils down to these 4 critical numbers. You've got the total workload for the motor, the required strength of the belt itself, the exact size of the engine you need to go by, and that all-important confirmation that your system's grip is strong enough for the job. This is the blueprint that turns all that theory into a real working machine.
It just goes to show that behind something that seems as simple as a conveyor belt, there's this incredible world of physics, math, and just brilliant problem solving. It really makes you look around and wonder, right? What other everyday machines that we totally take for granted are hiding this same level of engineering genius?
The scale of these applications is just mind-blowing. Think about digging a new subway tunnel deep under a city. How do you get all that dirt and rock out? A vertical sandwich belt. Or lifting tons and tons of ore every single hour from a mine that's a mile deep? Yep, sandwich belt. Loading gigantic cargo ships, feeding power plants? This simple, elegant idea is at the very heart of modern industry. And that brings us to the ultimate party trick. 90 degrees, a pure, straight-up vertical lift. For handling bulk materials, this is the holy grail. It lets engineers design and build facilities with a much, much smaller footprint, saving space, time, and a whole lot of money, all thanks to an idea inspired by a sandwich. So, the next time you look at some simple, everyday object, just ask yourself, what problem could this solve? The sandwich belt conveyor is just the perfect reminder that the most amazing, elegant solutions are often hiding in plain sight. They're just waiting for somebody to come along and see them in a totally new light.